Alright, let's talk about limits as x approaches infinity. Here, there's a couple basic limits that we need to talk about. So I'm going to write them down. So, basic limits to tattoo to your brain. And if you're dyslexic, you could tattoo it to a guy named Brian. So here, we have the limit as x approaches infinity of 1 over x. Now, once, you could try this in a calculator. When I think of infinity, I just think of a really, really, really large number. It's not an actual number, but I just think like, okay, I'm plugging in a super huge number. So 1 over a super huge number makes the whole entire fraction really, really tiny. Like the denominator dwarfs the numerator, and so this whole entire fraction gets really, 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 really small. So it goes to 0, the whole entire thing. You can try that by going 1 divided by and then type in some really, really huge number, and you should get like 0.0000000, or like something really, really small, 0.001 or 0.00369 or whatever you have. It'll be very, very, very small. Same exact thing happens with the negative as x the limit as x approaches negative infinity. Even though this is negative down here, it's still corresponding to something that's really large but negative, and then it dwarfs the whole entire fraction, so it goes to 0 as well. Now, some people, this is like to remember, but some people like to think of, oh, wait a minute, I know the graph of 1 over x. That just looks like this, where it approaches infinity. Yeah, this just looks like this. Well, if I approach infinity from my graph this way, that means I have to be on this part of my function, and my y value is approaching the horizontal asymptote as 0. And same as when I approach negative infinity. Even though this is a negative number, I'm still approaching 0 just from the underside. So this is the graph of f of x equals 1 over x. So if you just remember those two things, they tell you that this is the limits as x goes to infinity. So that's something to remember. It's very similar also. It's very similar with, let's do it in green, limit as x approaches infinity of 1 over x squared. That would still be 0. It's very similar to limit as x approaches, I can make it negative infinity of, like, I don't know, 16 over x cubed plus 3. All of these are very, very similar just because the denominator is still getting super, super large, like negative or positive, and the numerator is staying still. Alright? So these are similar. These still go to 0. Similarly go to 0. So that's for that part. What do I want to add? Let's talk about this special limit. This is a cool one. So the limit as x approaches, let's say, positive infinity of sine x over x. What does that equal? Now, if I just do direct substitution, it doesn't really make sense on the inside here. It doesn't really make sense. But I know that the graph for sine of x, so let me draw that real quick. I know that the graph for y equals sine of x just oscillates back and forth forever and ever in the other direction as well. Something that's key is this function never gets higher than 1, and each peak is no higher than 1, and each valley, each low point, is no lower than negative 1. So sine of x always bounces between always bounces between 1 and negative 1. Okay, so there we go. It always bounces between 1 and negative 1. Now, what about the bottom? What happens to the bottom? I haven't really talked about the bottom part. Well, if this is going to infinity, then this is just getting super, super large. it's kind of similar to these limits, right? The bottom is getting super, super large, and the top is staying relatively small. In this case, the top, well, it's still staying relatively small. It's just the value is changing in, like between negative and positives, right? So here, this is kind of what happens. You can think of sine of x as staying relatively small. So what do we have? We have the sine x stays small in quotations because it's changing. It does stay small as x approaches infinity. That means for sine of x over x, the numerator stays pretty small, and the denominator grows without bound. So this just grows and grows and grows and grows and grows. So much like this, the limit as x approaches infinity of sine of x over x, that equals 0. And if we were to graph this, this is actually what it would look like for y, like let's say y equals sine of x divided by x. If we were to graph this, actually, it crosses the y-axis at 1, and then just dips below, dips above, dips below, dips above, and it just oscillates back and forth, but the oscillations get smaller and smaller and smaller. It forever oscillates, but it's still going towards 0. And then same in the other direction, but I'm not going to draw that part. So, yeah, as x grows infinitely large, the whole entire ratio, the whole entire fraction, goes to 0. So that's that. Well, that's kind of nice. I like that one.